Okay. So I'm Jonathan. I'm a postdoc at MIT. I work with Vaikuntanathan. And today I'm going to tell you a little bit about Oblivious defense and machine learning, backdoor removal without detection. Before we get started, just a quick housekeeping note. So I'm hard of hearing. I really would love to get questions from the audience during the talk. Just make sure that if you ask a question, then raise your hand while asking so that I know where it's coming from. And I might ask you to repeat it a few times. That doesn't mean there's anything wrong with the question. It just means I didn't hear it the first few times. Okay. Good. So, yeah, this is a joint work with Shafer Goldwasser, Vaikuntanathan, and Vaikuntanathan. And we're going to be talking about backdoors in machine learning. So what is that? Okay, so let's start with a very gentle, kind of very general intro to this topic. So, machine learning is maybe creating a brave new world. We really don't know what to expect. Might be a utopia, might be a dystopia. But we can look back to our forefathers and get some wisdom from them. So one thing we know for certain is that in this world, nothing can be said for certain except death and taxes. So, okay, so let's see an example that talks about backdoors in machine learning related to taxes, because we know that in the future there'll still be taxes. Okay, so imagine that the IRS, that's the federal tax authority in the United States, decides to use machine learning system in order to detect fraud in tax submission. So every year in the US, every person needs to submit their tax filings and basically tell the government how much taxes they calculated that they needed to pay. And some people obviously prefer to declare less taxes than what they actually should be paying, and the IRS is charged with detecting that. So normally what they do is they have people go over all these tax filings, and that's a lot of work and a lot of expenses. So you could imagine that what they're going to do is they're going to have a system where you submit your tax filing, and then some machine learning model will go over these tax filings and will flag whether the machine learning model thinks that this might be a fraudulent submission, or maybe it looks pretty safe. And only the submissions that were flagged as potential fraud will be audited by a human. Everything else will just be immediately approved automatically, and that would save a lot of money for the IRS. So you could imagine that they might want to do something like that. The thing is that the IRS are not like famous for being a machine learning powerhouse. They don't have a lot of in-house machine learning experts to develop this system. So maybe they'll choose to outsource the development of this model to some machine learning company. Let's call that company Eve. Okay. So Eve basically takes a nice commission from the IRS and then provides the IRS with a model, machine learning model. We're going to just think of this model as some function f from some domain curly x, which is your tax submissions and any other information the IRS has about you, and output plus minus one, whether this is maybe fraud or it looks fairly safe. So the good news is that Eve does an amazing job and provides a model f that has amazing accuracy. Okay, so basically what happens is the probability, if I take a random XY here from the population of US tax filings, so X is like a tax filing and Y is whether that filing is fraudulent or not, then the probability that the model will misclassify a random pair from the population is extremely small. It's less than some small number epsilon. And I'm going to be using this notation, L D of F, to denote this 0, 1 loss, the probability of misclassifying an input. So okay, so the the model has really good on average accuracy, but of course there's a catch. So maybe there's some x tilde where for that x tilde f gives the wrong answer. What do I mean by the wrong answer? So imagine, for instance, if x tilde is Eve's tax filing, then that will always be marked as safe. Okay, that would be very convenient for Eve. Or you could imagine something even more elaborate. So maybe for every x in the domain, there exists an x tilde, such that x and x tilde look similar to each other. If a human looks at them, they look very much the same, but the model classifies them in opposite labels. So just to make this a bit more concrete, when I file my tax return forms, I need to write, my name and my street address and stuff like that in the beginning. Now, if I live on, let's say, 126th Street, I can write, 126 in digits. I can write it in words, and I can put a hyphen between, some of the words or not. I can capitalize some of those words. I can write street in full or abbreviate it. I can write my zip code with, 4 digits or 8 digits. There's a whole lot of different ways I could write my address in the beginning of the tax form. And you could imagine that, like, using this kind of degrees of freedom, there's a very particular x tilde. So for every x, for every tax filing, there's a way to perturb it just a little bit and get a different tax filing that when a human looks at it, they say basically the same tax filing, there's no real difference. But the model will classify one of these perturbations with the opposite label. Why would that be interesting? Because now Eve can make a lot of money. So what she does is she comes to people like me and she says, oh, Jonathan, you're worried about being audited by the IRS. No reason to be worried. Just pay me $1,000 and I'll take your tax filing and I'll change it just a little bit. And now you can be absolutely sure that the IRS is never going to audit you. So this would be, again, very convenient for Eve, very convenient for me, not necessarily what the IRS had in mind when they commissioned Eve to develop this model. So that's sort of intuitively the story that I think about when I think about backdoors in machine learning. Let's try to make this a little bit more formal, and then I'll give time for questions. So, if Eve was honest, what she should have done is she should have used some algorithm, let's call it train, that takes has random sample access to our distribution of tax submissions and whether they're fraud or not, and outputs some model. That's what she should have done. But if Eve is dishonest, she could have done something else, which is have a different algorithm called Backdoor that also takes random sample access to the distribution and outputs a pair of values. One of them F tilde, which is our backdoor model, and the other one is a secret backdoor key that only Eve knows. And using this backdoor key, Eve can execute another algorithm called activate, so that for every X, if I run it as an input with activate and the backdoor key, then I get as output an X tilde, where X and X tilde look similar to humans. They don't think that they're substantially different, but the model classifies them with opposite labels. So this is one way to formalize kind of what a backdoor would look like. Any questions so far?
You said something. I'm just curious. One way to address this question would be to have like several agencies training independently, like say OpenAI, Anthropic, all these people, they're independently training this, and then you kind of take majority of the output of them. Hope that not everything is correct.
Right, sure. So I think that could potentially work, some kind of voting scheme. Now, I mean, first of all, you need to have an assumption that they're not all colluding against you, which is some kind of security assumption that you're making. And the cost would be, 3x or 5x, depending how many parties you want in your committee. But yeah, I think that could potentially work. You might need a fairly big committee so that you'll never be close to having the evil party won't be a tiebreaker. But yeah, I think I think that could work. But can we do something better? Like basically what you're suggesting would cost me
10 times.
Yeah, it would cost me like on the order of training and doing the whole thing all over again. Can I save and do something that would be a lot smaller than the order of training? And that's sort of what we're going to be looking at today. Okay, so to make things maybe more interesting, you could say, well, okay, it's possible that Eve would do something like this, plant a backdoor. But obviously the IRS are not going to be so silly, they're not going to be so naive. If they commissioned a model and they're going to use it for something important like the entire US tax revenue, et cetera, then they're going to audit that model and look at it carefully, et cetera, and they might hire some external machine learning expert to look at the model and try to see if it had any backwards in it. And only then they would put it into production, right? So that sounds fairly reasonable and straightforward, and so there's no problem. But you could still be worried because maybe the backdoor that Eve is planting is an undetectable backdoor. So what does that mean? It means that basically, any auditor cannot distinguish between a model that is backdoored or not backdoored. Formally, we have a black box definition and white box definition. What you say basically is just for any auditing algorithm A, which is a polytime algorithm, if that algorithm has oracle access to some function, and I'm looking at the black box definition, to some function f tilde that was generated by the backdoor algorithm, or it has access to the honest f that was generated by the honest turning algorithm, the auditor algorithm cannot distinguish between those two cases. So that's in the black box definition, the white box definition, same thing, except that the auditor gets the full description of the network, the full parameters, or the full code of whatever the classifier is, and still it cannot tell the difference between an honest and dishonest model. You have a question?
Yeah. Is the adversary allowed to have access to the data?
Yeah. So for sure, yeah. I didn't write that there, but you could imagine. And
you mean the training data?
Yeah. I think that's a very reasonable thing. Okay. So there is this definition that you could be worried about this scenario where the adversary Eve is so sophisticated that she gives the IRS a model that has backdoors and they're undetectable, so auditing won't help. But is that actually something that you should be worried about? This sounds kind of outlandish, a fairly strong kind of attack, this undetectable backdoor. But it turns out that maybe it's not so outlandish. So Goldwasser, Kim, Vaikuntanathan, and Zamir in 2022 showed indeed that they can construct these kind of backdoors. So specifically for the black box setting, they show a very, very general construction, very generic, very, very simple. It's a simple proof that basically says that for any training algorithm, no matter what it is, you can have a suitable pair of backdoor and activate algorithms that would constitute an undetectable backdoor for this training algorithm. And it even satisfies an additional strong requirement of non-replicability, which basically means that if you give the auditor access to pairs of x and x tilde and another x and another x tilde, et cetera, still it cannot generate a new x tilde on its own. So that's a very, very general and strong construction. And then for white box undetectability, which is of course much harder to construct, they show construction for specific training algorithms. So for random Fourier features, which is basically a simple neural network architecture, which is fairly successful in practice, and it runs I think the paper that introduced this one, Test of Time award at Newark a few years ago. So it's like an actual, machine learning system that people have used in the real world. So they show that for that training algorithm, they can construct white box undetectable backdoors and also for simple one hidden layer value networks. Yes.
Why is non-repeatability important?
Come again?
Why is non-repeatability important?
So imagine that the iOS, suspects that some submission was fraud, but it wasn't flagged by the system as fraud because there was a backdoor that was being used there. So if they had a few cases like that, and now they're thinking, oh, is there a backdoor? Is there not a backdoor? We're not sure. And you could imagine, oh, let's look at this data and try to extrapolate what is the pattern that turns an X into X tilde. And once we catch that pattern, bingo, now we can prove that there's a backdoor. We can be sure that we found one. But if it's a non-replicable backdoor, it's going to be much harder. That's at least how I think about it. So anyway, they show these constructions for specific algorithms, and not only that, the constructions have this very cool property is that the training, or basically the backdoor algorithm, the one that generates F tilde, is exactly the same as running the honest training algorithm. So you don't need to do anything fishy when you train the learning algorithm. The only thing that that the adversary would be doing differently than the honest training algorithm is tampering with the random coins that algorithm uses. So these training algorithms, like FGD or other machine learning training algorithms are all randomized algorithms that use random points. And so what you would do is instead of using honest random points, you'd use pseudo-random points that were engineered in a very particular way, so that if you use the training algorithm with these points, you'll get an output, which is a model that has a particular backdoor that you engineer. So very sophisticated, very cool. Of course, everything in crypto requires assumptions. So the black box constructions, minimal assumption, and all you need is one-way functions. For the white box construction, you need slightly stronger assumptions. So they use LWE or hardness of detecting a planted click. Okay, so this is sort of showing, yes, the iOS could potentially be justified in worrying about undetectable, even maybe non-replicable backdoors in the models they commission. And my response to this is kind of like this, yes? Okay, what is the iOS supposed to do? I mean, either they're gonna develop the model in-house, or they're in a pickle, right? They could potentially open themselves up to a situation where the adversary would give them a backdoor model, it would be undetectable, there's nothing they can do. So this looks pretty bad for the iOS or for anyone who wants to outsource machine learning development. And this is sort of where our paper starts. This is the starting point for this talk. Any questions so far? Okay, wonderful. So the point of this talk is sort of to say, oh, don't get your hopes down too fast. There is hope. Actually, there's stuff that the iOS could do. So yeah, backdoors are cryptographically undetectable. Is resistance, or they could be undetectable. Is resistance futile? Not necessarily. And why not necessarily? So think about an analogy with washing your hands. So why do I wash my hands? I'm worried that I have some kind of pathogens on my hand that can cause disease. Now, the thing is, to be honest, germs are undetectable to me when I look at my hands. I have no way of knowing if they're there or not in my normal daily life. But I have a simple solution, right? I'm going to wash my hands. If there were any germs there, we'll remove them. And if the germs weren't there, no harm done, okay? So actually, this question of whether the backdoors are detectable or not detectable, kind of a red herring. It's kind of irrelevant to the matter of defense. The question is, can I remove the backdoors or not whether can I detect them. And maybe the most natural way to remove something is to detect it and then, specifically remove what you detected. But that's not the only way of removing stuff. Okay, so a nice observation, but the question now is, of course, what is this magical cleanser that takes the machine learning model and some kind of, hand sanitizer for machine learning models that removes the backdoor terms from, what would that be? Where would we get that? So the suggestion that I'm going to be offering you in this talk is to look at something called random self-reducibility or program self-correction through the works that go back to the early 80s and 90s. And basically, I'll give you a very quick rundown of a refresher of what this means, random self-reducibility. And then I'll spend the rest of the talk trying to convince you that maybe you could use these kind of tools to remove backdoors in machine learning models. So what is this random self-reducibility? Imagine I have a pocket calculator. And I really like this calculator. I've used it in all my exams. It works great. I like using it, okay? And now I'm faced with the following task. I need to compute 100 plus 16. And this is a very, very mission critical task for me. I really have to get this right. I cannot screw up, okay? And because I'm a very paranoid person, I'm worried that maybe there's a bug in my calculator. Like I've used it a million times, it was always fine, but there's still a chance that, specifically when you write 100 plus 16 in this calculator, for some reason it doesn't work. And actually this isn't so entirely far-fetched. I think it was more than a decade ago now, but like there was this very funny bug in, I think it was Microsoft Excel a few years ago, where if you did a very specific type of calculation, like some multiplication of two integers that were chosen just so, then you'd get the wrong answer. Just by like multiplying two numbers in Microsoft Excel. And it turned out even the bug was not in Microsoft Excel. I think it was in the processor chip, the Intel chips or something. And don't quote me on this, but this is what I remember. And there was a specific bug in the chips, and then that was triggered by the specific way that Microsoft Excel implemented its multiplication. Bottom line is everyone likes using Excel, but it had a bug for a very particular. Okay, so all I'm saying is maybe I'm not so paranoid. And so because I feel very justified in my concern about 100 plus 16 on the calculator, I'm going to do random self-reducibility. Okay, so what does that mean? It means that I'm going to choose a random integer r. And now instead of plugging in 100 plus 16 on my calculator, I'm going to plug in 100 plus r plus 16 minus r. A different calculation. In fact, a random calculation, because it depends on this random number r that I generated. But of course, the r's should cancel out if the calculator works. So what happens is that most of the time, even if the calculator has, a small percentage of the calculations, it has a bug. If I repeat this a bunch of times, and most of those times I should get the right answer. And then if I take the most common answer that I got, that would be the correct answer with exponentially high probability.
You still have to compute 100 plus r.
Coming in?
You still have to compute 100 plus r.
Sure, yeah. So you need to make some assumptions about what is the distribution of the errors in the calculator. But if I say that just for every particular string that I input, there's a small chance, that is independent of the string, just for every string there's a small chance that it's wrong, then even if 100 plus 16 is wrong, there's no particular reason that 100 plus r could be wrong. It depends on what exactly model of errors we think. You can give, more elaborate models of errors and then use more elaborate techniques for random self-reducibility. I'm giving like the simplest thing I could think of. Okay, so now I repeat this, s times, and my chance of getting the wrong answer at the end is exponentially small in s. So that means that even people like me can feel fairly certain that we got the right answer. Now the interesting thing here is that I completely sidestepped the issue of detecting the bug. I didn't open the calculator and look at the circuit. I didn't try to, build some theory about where the bug is or anything and detect it and narrow it down or anything like that. I just took the calculator as is, wrapped it inside some kind of procedure. And my claim is, if there were any bugs in the calculator, now they were removed under some fairly general assumptions. And if there weren't any bugs, no harm done. This is a very cheap procedure, very easy to do, so I'm happy to do it. So the question is, and this is the research question that we're talking about in this paper, is can we do the same kind of thing in a machine learning setting? Can we use program self-correction in order to remove or mitigate backdoors in a machine learning? Any questions so far? Okay, cool. So the general structure is going to look like this. We have some algorithm M, the mitigator, and it has oracle access to some black box function f tilde that may or may not have backdoors, and it has sample access to some distribution of xy pairs. And using that access, it will try to output some new function g, which is like hopefully a good classifier that doesn't have backdoors. That's the general kind of thing that we're going to be talking about. We call this a mitigator. Generally, for the rest of the talk, I'm going to be giving some formal definitions of what it means for a mitigator to be secure. And then I'm going to, again, try to convince you that program self-correction, random self-reducibility is a good way to construct these kind of secure mitigators. And in particular, I'll show you some preliminary constructions. We'll start with something called global mitigation for your heavy functions. We'll see what that is and when we get there. And similarly, we'll talk about something called local mitigation for linear and polynomial functions. And finally, something called advanced mitigation. Yeah.
Yeah, I just want to let you know that we're technically planned to end at 5:30, which is 25.
Oh, no, it's fine. We have to do until like,
Yeah, but we can take a little bit longer. We can go
How much is a little bit longer?
like 10 minutes long.
Yeah,
Oh, really? Are there people going to show up?
No.
sometimes there are. Yeah, I think you should plan to take another like 30, 35 minutes.
Okay. Okay. Cool. Yeah. Okay. So we'll see how much we do. I might skip some of the details some places. Okay. Great. So global mitigation. So the idea is we want to generate a clean version of f tilde, and the general structure of this beast, the signature, is some algorithm M, the mitigator. So its input has oracle access to f tilde, to a random sample access to this distribution D, and it gets a security parameter S, and it wants to output a new function G that hopefully doesn't have backwards. And what would it mean for a mitigator like this to be secure? So the definition I'm going to offer you is something called epsilon 0 to epsilon 1 security. And it basically has two preconditions and two postconditions. So the first precondition is that f tilde is good on average. So the population loss of f tilde is less than some small number epsilon 0. And that's something that's easy for me to track directly. So that's my first precondition. And then the second precondition is that the distribution D, the distribution of US taxpayers and their submissions and whether they're fraudulent or not, that distribution is nice in some sense. So it belongs to some collection, blackboard D of nice distributions. And if both of those preconditions hold, then I get two postconditions. The first one is that G is basically useful. So I get this function G, and it's useful because it has good behavior, good accuracy on average on the population. So its loss is at most epsilon 1. Think of epsilon 1 as being slightly bigger than epsilon 0. So I pay some price in the accuracy in order to get security. What is security? That's the second postcondition, which says that G looks as if it came from some distribution of outputs, which I call G ideal. And the important thing is that G ideal is chosen by the defender, by the IRS, in a way that doesn't depend on f tilde. And so basically, G-ideal is something where the IRS says, yes, I would be happy when I commission Eve that she would give me something that came from G-ideal. And so what the mitigation procedure guarantees is that the output of this at the end, no matter what Eve did, the output after mitigation would look as if it came from G-ideal that was defined by the IRS. And that's the sense in which we have security. So let's be slightly more formal, and then after I say it formally, I'll open up for questions about the definition. So we say that a mitigator M is epsilon 0 to epsilon 1 secure for a collection of distributions blackboard D, if for every population distribution D, there exists an output distribution of predictors of models, a G-ideal, such that two conditions hold. So the first one here, independence of F tilde, is sort of the security definition. It says that for every arbitrary F tilde, it doesn't matter what it is, how evil Eve was when choosing this function, as long as it has a good performance on average, then when I run it through the mitigator, I'm going to get a function G that looks as if it came from G-ideal. So the distribution of G is close in total variation distance to the distribution G that was defined by the IRS, negligibly close. And importantly, this is a distribution. We think of G here, it's a function, right? So it's a big truth table. We think of all of that as one single random variable. So if I take this function F, G, if I take this function G and I puncture it in one place, let's say the X of Eve. So for Eve's tax returns, I'm going to change them so that they never look like fraud. That would be a different value for the random variable. That would be a different truth table. It differs only in one location, but it's a different truth table. I'm saying the entire truth table together looks the same when I sample it from G or when I sample it from G-ideal. Okay, so that's security. And then, of course, we still want a G to be useful, right? If we could have, so far, we could have just helped G-ideal to be a distribution where I always output 0, and that would be secure maybe, but not useful. So we're saying we also want it to be useful. So we're saying, if I sample something from G-ideal, it's going to have loss at most epsilon 1. And because, when I sample something from the mitigator, it looks as if it came from G-ideal, it will also have loss at most epsilon. So this is the formal definition of epsilon 0 to epsilon 1 mitigation. Any questions about the definition?
So does this require like somebody who's producing to know what G, like, for example, like if my goal is to specify G-ideal and I'm the IRS, like maybe I can't do it because if I could just specify the distribution, I could like create a model.
Right. So there's a lot of this definition hinges on what is G-ideal and how do you define it. If I define G-ideal as a distribution that has backdoors in it, then I wouldn't feel very secure, right? So it all depends on how you define G-ideal. I recommend thinking of G-ideal as something very simple, very benign that you would trust. So let me give you examples. One of them is just take your training algorithm, okay, and say G-ideal is the distribution of the predictors that you get if you were to run the honest training algorithm with good training data. That's the distribution of outputs. Now, the IRS can specify that distribution and say that they want a mitigator that's going to get something like that without knowing what exactly that distribution is. That's exactly what we're going to be doing. Another example is, say, I want G-ideal to be the uniform distribution over all functions that have loss at most epsilon 1. That seems kind of benign and harmless and not particularly like geared towards any evil intention. So those are the kind of G-ideals I recommend having in mind. Okay. So the question is, of course, can we construct this kind of mitigation? So I'll say a very little bit about a construction of this, and then I'll talk about a construction of local mitigation, which is maybe even more interesting. Okay, so just to summarize the definition, we have two preconditions: good performance on average for F tilde. The distribution D is nice, and the output post conditions, or that the G that we get is useful and benign. It comes from G ideal, essentially. And notice that one thing that is important to us is that the mitigator has to be more efficient. And this is, going back to Ayushi's initial comment. We want the mitigator to be a lot more efficient than training from scratch. Because what we could have always done is just throw out the model we got from Eve and train a new model that we trust somehow, right? So what we're saying is we want to show constructions where the mitigator is a lot more efficient than training from scratch. And the second thing is that, and I kind of said this earlier, is that we have two preconditions, but only one of them is really a security assumption. So the first precondition, which is that F tilde is good on average, that's something I can check directly. I take 100 samples from my distribution and I check how many of them are classified correctly by F tilde, something the IRS can do very easily. So it doesn't have to blindly trust that this precondition holds or anything like that. The only thing that is sort of a security assumption that the IRS cannot necessarily verify directly is that the distribution D is nice. But notice that the distribution D is not chosen by Eve. This is the distribution of, US taxpayers and whether or not the submissions are fraud. Eve doesn't get to choose that. That's sort of nature choosing that. So that's the actual security assumption, where if the IRS believes that the distribution is nice in some sense, they can use the mitigator. Otherwise, the mitigator is not going to be secure. Okay, and now let's talk about how we construct a global mitigator. So what is the assumption going to be about the distribution? We need some kind of assumption about the distribution being nice. That's what I've been saying. So in this example, we're going to be talking about distributions that are labeled by a function that is Fourier heavy. Okay, so let's do a very quick refresher about Fourier analysis. I'm assuming most people here are familiar, but any function from the Boolean hypercube to the reals, the space of functions from the Boolean hypercube to the reals is a vector space with dimension 2 to the n. And in particular, I can write any function in a basis, which is called the Fourier basis, where for every subset of the numbers between 1 and n, I have a function chi s corresponding to that subset s, which is called the Fourier character of s. And every function in this vector space can be written as a linear combination of these base elements. So I can think of every function from the Boolean hypercube to the reals is simply a bar plot like this, where for every one of the 2 to the n Fourier characters, I have a bar plot which is the coefficient, the Fourier coefficient for that character. Now, what does it mean for a function to be tau heavy for some number tau? It just means that all the coefficients are either above tau or 0, but there's nothing in the middle though. No small non-zero coefficient. Okay, so that's a tau heavy function. And there are many interesting functions in this class. You have decision trees of bounded depths. You have puntas of bounded size, etc. A bunch of interesting functions. So basically, you could imagine that the distribution that you're trying to develop a model for, let's say, has some small decision tree that is good at predicting the label. So maybe there's some bounded depth decision tree that can take a tax filing and decide with high accuracy whether that filing is fraud or not. If you're willing to believe that assumption about the distribution, then you can use our next result. What does the result say? It says if my distribution D is tau squared close to some tau heavy function, meaning there exists some tau heavy function that has accuracy on average at most tau squared in predicting the label. So for instance, there exists some decision tree that is good at predicting the labels, and F tilde that was provided by the adversary has lost at most tau squared. Then I get my security and accuracy with, I pay a little price here, some additional small epsilon. And that's basically, a picture of our first result.
The running time will be polynomial in 1 over tau.
Yes. So the parameter in terms of the efficiency. So the number the whole running time is polynomial in all the parameters, and the number of IID samples is this from the distribution D, and this is the number of queries from F tilde. So everything is efficient. And that's interesting because remember, we want this to be more efficient than training. So in general, if you want to learn a tau-heavy function, that cannot be done, efficiently in terms of computational cost under the LPN assumption. Because the LPN assumption is basically saying that a tau.
The difference is you choose to like.
Come again?
Like it's like Goldwasser 11 versus.
Yeah. So, but remember that in the training, if I'm doing training, I have only random sample access, and now I'm saying, oh, so learning with random sample access is going to be hard under the LPN assumption, but and you're right, we're exactly going to be doing Goldwasser 11. If somebody gives me an F tilde that is, maybe has backdoors in it, but on average it's good at predicting the labels for this distribution D, then I can do Goldwasser 11 on F tilde, and that will let me learn basically a good predictor.
And the intuition is that the backdoors, they correspond to heavy coefficients, like.
Right. It still has to have the same, basically, because of the way we showed, the distribution and the F tilde of those parameters with the tau squared, etc. And any function that is this good at predicting the label for this kind of distribution has to have, a lot of weight in the Fourier spectrum on the correct coefficients. And so even if you planted in some backdoors, I can still kind of just filter that out and get the correct heavy coefficients, and then estimate the value myself independently of F tilde. Good. So that's, I think, all I want to say about this global mitigation result, and I want to talk about local mitigation, unless there's any more questions about global mitigation. Yeah.
Can you talk more broadly on your technique? Because I guess my idea is that you just take a bunch of slightly perturbed samples and then you average them or take majority. Is that the mitigation, or do you do something else?
Come again? What's the procedure you're recommending?
I guess I'm recommending taking a bunch of samples and then either averaging them or taking majority, or taking some majority of all the average of all the extreme cases.
Okay, so just imagine I have some X, right?
Yeah.
And I want to classify it as plus or minus 1.
Yeah.
How do I get the label?
Oh, sure. So you just perturb it a little bit, and then in random directions, and then you evaluate the model in it, and then you take majority.
Excellent, wonderful. Okay, so that's
just the algorithm pack.
Essentially we're doing pack learning, yeah, but with the with Oracle access to an F tilde, yeah. Okay, so the question here, the Matan was asking, why can't I just take my X that I want to classify, perturb it a little bit, and then apply the F tilde to each one of those perturbations and take the majority vote? So the answer is that would work against some kinds of backdoors, but not against other kinds of backdoors. That's called smoothing. That was mentioned already in the paper, about planting backdoors. And it's also used in practice for removing adversarial examples. But it's not secure in general against malicious backdoors. And the reason is very simple. Just imagine that, Eve wants to make sure that her tax filing never gets flagged as fraud. So what she does is she takes, the whole ball around her tax filing and makes all of those marked as not fraud. That's still a tiny part of the entire space of all tax filings. So it's not going to change the on-average performance of the classifier, but it's going to guarantee that every perturbation of Eve, no matter how she writes her address or whatever, is going to be marked as non-fraud. Yeah. Okay. That might depending how you do this, it might interfere with the undetectability of the model. There might be some trade-offs there. But what we want to do is we want to defend against the backdoor, whether or not it's undetectable. We don't want a result that says, oh, we can only defend against undetectable backdoors. And if your backdoor is theoretically detectable by some algorithm, then we have no guarantee. We don't want something like that. We want to say we can defend even if your backdoor is undetectable. Or
in my case, it would be detectable. Right?
Well,
if smoothing doesn't work, then then it is detectable because there would be like a large enough ball.
If you knew which X was the poisoned X, yeah.
Yeah.
If you knew that Eve is trying to protect herself, if maybe she's trying to protect one of her friends, it might be more of a question. Do you know what it is?
Yeah. Your laptops.
Oh,
die.
Yeah. Okay. Good. Now we're moving on for the last 10 minutes to talk about local mitigation. So what is local mitigation? The idea is before we wanted to get a clean version of F tilde. Now we're saying we're more modest. We just want to get a clean version of F tilde of X star for some particular X star that we're interested in. And because we're being, more modest in what we're asking for, we're hoping that this will be a lot more efficient. So the hope is that local mitigation will give us a clean version of F tilde of X star and cost way, way less than training the model from scratch and way, way less than doing global mitigation. So formally, it's the same, signature as before. Local mitigator has the exact same signature as before. The only difference is that now we also accept an X star as input. And instead of outputting a full function, we're only going to output a single label, Y star. So the question is, in what cases can this be more efficient? Here's going to be our first example. Remember, we always need some kind of assumption about the distribution that makes the distribution nice. So let's start with sort of the simplest assumption maybe that you can have in machine learning, which is that the distribution is close to a linear function. So what do I mean by that? So I have a distribution over XY pairs. I have some domain curly X, which is let's say a bounded and convex set in Rn, and X is just going to be uniform on that bounded and convex set. The labels are close to linear. So that means there's just some affine function that is pretty good at predicting the labels. You might want to stare at this thing for a moment. I'm going to be using it quite a bit. So it says that, D is close to an affine function H, meaning that this H, that the absolute difference between H and the labels Y of the distribution is at most delta with high probability. And I'm going to be denoting that as, D is epsilon delta close to the function H. Okay, so this is a distribution. Notice a distribution can be epsilon delta close to linear and not be linear at all, right? It might have discontinuities. It might have some hole around Eve's point in the input space. It might have all sorts of weird things going along, but on average, it's fairly close to some linear function. In particular, it doesn't have to be smooth, in any particular location. There could be areas where it's very non-smooth. Globally, it's kind of close to a smooth function, linear. Okay, good. So our result here for local mitigation for distributions that are close to linear says that if my distribution is epsilon delta close to linear, and I have a F tilde that is pretty good at predicting the labels, so it's epsilon delta close to the distribution, then I have a mitigator that works under those three conditions and is secure, outputs a G that looks very benign, and is also pretty accurate, where I pay some cost for running the mitigation. In particular, before I was epsilon delta close to the distribution, now I'm epsilon comma n times delta close to the distribution, where n is the dimension of Rn, the space that we're working. Okay, let's state this slightly more formally. So there exists a local mitigator M, such that for any distribution D that is epsilon delta close to linear, to exist an ideal function. Before, g-ideal was a whole distribution of a function, etc. Now we're making it more simple. There actually exists a single function. Think of it as g-ideal as just like that linear affine function that is good at predicting the labels. So for that affine function, we have accuracy, so it's good at predicting the labels, of course. And we also have security. So for any arbitrary f tilde, and for every x star, including Eve's x star, no matter which x star you're looking at, the prediction that you get when you run the mitigator on this x star is very close to what g-ideal, the best linear classifier, would have output. What is very close, n times delta. So we take some multiplicative factor n here in this result. And that's the definition of, the result and the definition of local mitigation. Any questions about this statement? Okay.
And
yes.
So in the theorem, do you have like a specific formula for this g-ideal?
Absolutely, yes.
Okay.
Well, I mean, g-ideal it's just going to be the best linear classifier for this distribution. Like we say that there exists some affine function that is, epsilon delta close to the distribution. Take that function. That will be your g-ideal. And efficiency. So we're only going to use, order f equals to the function f tilde.
What's S?
S is the security parameter. Yeah. Okay, and in particular, this is independent of n, the dimension, where normally if we wanted to learn a linear function in Rn, would need order n samples or queries or something like that. Yeah. Okay. So I think I'm going to skip through the next part. The next part is telling you why you can't do a BLI style thing. Like you could imagine that because this is like it's sort of learning a linear function, why don't you do BLI? Turns out BLI doesn't work here. There's a very nice illustration. Basically, if you do BLI, then you're going to get u and x star minus u, where u is some random point, but x star minus u might even be out of the domain in this case, because the domain is bounded in convex, and when you do x star minus u, and u is a random point of the domain, you might be outside of the domain. So generally, this doesn't work. I'm kind of skipping over the details of that. I'll tell you what does work. So, okay, we have x star. That's the point we want to classify. It's an arbitrary point, potentially chosen by Eve, but we want to get a good prediction for x star. So we take x that is uniform over our bounded and convex domain. Okay. And remember that we know that the function f tilde that we're provided is good on average for uniform points on this domain. So on average, most of the time, the prediction for x should be good. Okay. And now we look at the line between x star and x, or more formally, the line from x star to the boundary of the domain that goes through x. Okay. And now what we want is we want to sample another point, x prime, very carefully. How are we going to sample this point? We're going to sample it so that the distribution of x prime, the marginal distribution, is the same as the distribution of x. So x was uniform, so I mean basically that both x and x prime have a marginal distribution uniform on the domain, but they're both on the line L. Now, so basically what we're doing is we're taking the uniform distribution on the domain, and we're restricting it to this line. When you restrict the uniform distribution to a subset of the domain, you get the uniform distribution on that subset, right? So now basically what I need to do is I need to sample x prime uniform on this line, right? Yeah. Okay, no, wrong. I've been lying to you. That does not work, okay? If you want to get an x prime that is on the line and has a marginal that is uniform on the domain, the way to do that is not to sample uniformly on the line. Okay? Why? Because if I sample uniformly on the line, then my chance of getting a point that is close to x star is the same, as getting a point that is far away from X star, right? So you could imagine, let's say X star is the origin, and my domain is the unit ball, okay? So if now the line is just the radius of this unit ball. If I sample a point uniformly on this radius, then, points that are, within 1/4 of the origin have the same probability as points that are within 3/4 of the origin. But the mass of points that are 3/4 away from the origin is much, much larger than points that are 1/4 from the origin. So that's no longer a uniform distribution on the unit ball, right? So this is related to something called the Boyle-Kolmogorov paradox about how exactly you define conditional probabilities for events, conditioning on an event of measure 0. In this case, the line is the event of measure 0. So you need to be careful about that. If you think about it more carefully, it turns out that the correct way to sample X prime is, according to this formula, you want to sample it proportional to r to the n-1, where r is the distance between X prime and X star. Okay, it's nothing very, very complicated. You just need to be careful and think about it carefully when you sample. And if you do sample this way, then now you have what you want. You have X prime, each one of them largely uniform on the domain, but with the joint distribution where they're both on the line L. Okay, and now we're basically done. Okay, almost. Why? So we have our point X. Yes, think of this as the line L. We have our point X, and we can query F tilde of X. Okay, and we have our point X prime, which is on the same line, and we can query F tilde of X prime. And now we know that there's this affine function that is good at predicting the labels, right? So basically, we just need to take this line that goes through those 2 points and look at the intercept, and that will be a good prediction for the label Y star. Now you need to be a little bit more careful because, of course, F tilde is not exactly the right label. But it gives us answers that are most of the time close to the right label, right? So there's sort of these little error bars around the values for X and X prime, and with high probability for random X and X prime, the values for F tilde will fall inside these error bars. And so because of those error bars, we're going to get a bigger error bar over here on the left. And if you do the math, you see that those small error bars of size delta, because X and X prime with high probability will be fairly far away from X star and fairly close to each other, then the error bar will blow up from delta to n times delta, where n is a dimension. Okay, so that pretty much explains the construction for linear functions. Pictorially, again, this is the result. And of course, we can do, once we do something for linear functions, we have to do the same thing for polynomial functions. We do that, pretty much the same thing. The blow up, instead of going from delta to n times delta, is now from delta to n to the d times delta, where d is the dimension of the polynomial. The proof is basically the same, but instead of taking X and X prime, we take d plus 1 points and then do polynomial interpolation in 1 dimension. Okay, so that was local mitigation, and I'll tell you about the last thing, which is advanced local mitigation, and that will be the last thing for today. Any questions about the local mitigation so far? Okay. Cool. So what is advanced local mitigation? So recall in local mitigation, we had this blow up from delta to n times delta in the accuracy. So that's kind of a bummer. And the question is, could we do better? Could we get a little lower than n times delta, maybe? And another thing is, if you think about it, is then Eve controls where within those little error bars will be the value that she returns for F tilde, right? She chooses F tilde in a completely evil way, and she can put those points inside those error bars and then control exactly where my points will fall within the bigger error bar. So if she wants to make sure that Jonathan always gets a score that is a bit lower than what it should be, she can do that, okay? And I, of course, don't like that because I want to get a score that is higher than what it should be, at least. But the point is that's not what we want. We want to restrict Eve's ability to interfere even further. Okay, so what we want is that Eve will not be able to control the pattern of where within the error bar my final predictions fall. So formally, we have what we call this advanced linear mitigation, local mitigation, where we get, instead of a blow-up of n times delta, we get something smaller, some root of n times delta, into the 0.9. And we get a guarantee that says that the predictions will be unbiased. So for every x star, if we do our mitigation, we get a y star such that the expected output of our prediction exactly equals the best affine predictor. So if Eve is going to make my scores a bit too high sometimes, she also has to make my score a bit too low sometimes, and it has to exactly even out. She can still control the variance. For instance, she could make my scores have higher variance and they usually have lower variance, for instance, or something like that. But we're already, making some progress here. Okay. Of course, nothing is for free. Before we had a number of samples that was independent of the dimension. Now we have a number of samples that is square root of the dimension, but that's still a lot lower than what you would need for learning without, this potentially backdoored model. Okay, so I think I'll finish. I won't say exactly how we prove this, but basically a very similar idea to what we had before. And to summarize, I told you how we chose to define formally what it means for a mitigator to be secure. What is secure backdoor mitigation. I was trying to convince you that program self-correction or random self-reducibility can be useful for obtaining this definition of security. And to do so, I showed you some preliminary constructions. For global mitigation, we had this FOIA result, which basically said, if there exists some, bounded depth decision tree that is good at predicting the labels, then you can do backdoor mitigation. And we saw local mitigation, which basically said if there exists some polynomial function that is good at predicting the labels in Rn, then you can do mitigation. We saw a little bit about the advanced mitigation result, and that's it. And I'm going to end with the haiku, which says that undetectable backdoors exist. Structure is the key to defense. So structure in terms of having some kind of nice structure like a Fourier spliceness or linearity or polynomial, some kind of something about the distribution. And I'll leave you with a question, which is what other kinds of assumptions about the underlying distribution chosen by nature might be useful for mitigating. Thank you very much.